Hey folks, welcome back to Technicos, and I hope you folks are doing really good in your life learning Kubernetes. And you know what I'm thinking right now? There are two possibilities for which you have clicked on this video. One is you have been following the Kubernetes Zero to Hero series from the starting, and this is the fifth or sixth video. And if not that, the other possible reason is you don't know about services in Kubernetes, or you don't completely understand the flow and the concept of services in Kubernetes. These are the two possible reasons you are here. So don't worry, we will handle it. Okay. We will understand Kubernetes services from basics to advanced, everything step by step. And I can guarantee you, that's my guarantee, that's my promise, you will understand everything, every minor details. And what else I can say you is that if you need any personal help regarding DevOps jobs or DevOps SRE jobs or any support in terms of interview preparation or any professional support you need, you can directly reach out to me through my LinkedIn or my Instagram. I would prefer you reaching me through LinkedIn because I am mostly active there. So you can reach out to me and we can have sessions, we can have one-on-one sessions with you, and I will help you to grow in your career. Before that, please subscribe to my channel because that's something that motivates me to upload such content for you. And these contents requires a lot of time and effort because I'm the only person making the video, editing the video and publishing it. So it requires a lot of effort, and all these things I am doing apart from my full-time job. So you can understand how much effort it requires. So please subscribe to Technicos and also like the video. So we can start the series now. So let's start. Okay, so now we can start the video. Services in Kubernetes. Okay, let me click on this. Services in Kubernetes. So what we know currently that pods are ephemeral in nature. That means each time they get destroyed and recreated again, they will be having a new set of IPs. Okay, so every time a pod deleted and recreated, whether due to a crash or a node failure or rolling updates, it gets a new IP address. We know this. So we have a front-end application running in pod and a back-end application running in another pod. Okay, front-end and back-end. Now your front-end needs to talk or make connection to backend, then only we can say a full stack application, right? So now imagine your backend pod crashes and a new pod gets created again with the name backend. This new pod gets a completely different IP, 19.9, here it is 19.8 for example. Okay, just for understanding. Now the new pod is having 19.9 as a IP address, and your front-end application still has the old IP address hard-coded or cached. It tries to reach the backend application, but it keeps on failing. Why it keeps on failing? It keeps on trying, keeps on failing because it keeps on trying to the old IP address, and this problem will occur many times if you don't understand the concept of services in Kubernetes. So I told you that is very, very important. So there are actually two problems here. One is instability. The pod IP addresses are not stable. They change every time a pod restarts. Another problem is discovery. So even if you accept that IP change, okay, but your other pod have no idea, no automatic way to find out what is the new IP address. Okay, this is the core problem that Kubernetes solves using services. So let me remove all of these so that we can proceed further. So we discussed these two problems, these two done. Now, what is Kubernetes service? Okay, a service is a Kubernetes object that sits in front of group of pods. So a service is a object, Kubernetes object that sits in front of a group of pods and provides three things. Okay, So there are three main things that it is responsible for. One is a stable IP address that never changes even when the pods behind it restarts. Okay. The another thing is a stable DNS name. A stable DNS name, which means that the other applications can use to find your application, and a load balancing. Okay, it automatically creates or distributes incoming traffic across all healthy pods. So these are the three key benefits of using services. So before we move to this section, how services find a pod, we should understand more in depth on how a service actually works. Okay, if you are a beginner to this services, then it is difficult to understand. I can understand that, but I will make sure that you understand everything, every concept in Kubernetes. That is my promise to you. So think of a service as a permanent front desk or your pods. Okay, so for example, there is a office, and then in that office we have a front desk. Okay, each time a person comes, service is there. So client always talks to the front desk. So this is the client or a person. It talks to the service, and they never need to know which specific pod is handling their request or what that pod's IP address is. So with this architecture you can understand, I know this is a very bad looking architecture, but I hope for understanding purpose this is fine. POD. Okay, so this is a client, C for client. So what I told you, the think service as a front desk for your pods. Okay, so client always talks to the front desk, and they never need to know which specific pod is handling their request. The client comes in through the main door and talks to service. It does not care about what are the pods inside, what is their IP addresses and all. They talk with the service. Service takes care of handling pod's IP. So the service always also automatically tracks pod's health. When a pod dies and a new one comes up, the service immediately updates its internal routing table to send traffic to the new healthy pod. This happens automatically without any manual intervention. We are going to understand what is this routing table, don't worry. So I hope this diagram is clear. Once again I tell you, the client is coming to the front desk and it's talking to front desk. Front desk is redirecting the traffic to pods. Okay, this front desk is redirecting all these pods are behind the front desk, which is the service. Okay, now how a service finds pods, that's very important question. I told you na, if this is a node, if we are talking about this service as a front as for service, and these four are pods, if we are saying that how service finds pods at the first place, that's the first question. So it finds using two common thing. One is labels and selectors. Important concept. Okay, so every pod in Kubernetes can have labels. Labels are simple key value pairs. I have mentioned here, labels are simply key value pairs attached to objects. For example, this is how you mention in the YAML definition file. So you have a label colon app name as backend, environment, production. Okay, so every pod in the Kubernetes can have labels, and then in the service which has a selector field, the selector defines which labels a pod must have to be included in this service. So in selector we have the same application name as backend. Okay, I hope this is clear to you. So what is happening here? When this service receives traffic, it only sends the traffic to pod that have the label as app backend. Okay, if a pod does not have that label, the service ignores it completely. This is very important. I am again repeating, if at all a pod does not have that label, the service ignores it completely. This is a powerful design which means that services and pods are loosely coupled. So this I have already mentioned here. Services and pods are loosely coupled. Okay, so you do not need to configure a specific pod in the service. You just define which label to look for. When a new pods are created with matching labels, for example, by deployment scaling up, the service automatically starts routing traffic to them. When pods are removed, the service automatically stops routing to them. This is the whole flow of how service finds the pod. And in the whole flow, there is a critical point here. If your selector does not match any pod labels, the service will have no endpoints and the traffic will fail. So let's understand this service endpoints. So every service automatically creates and maintain an endpoint object. Okay, this endpoint object is a list of actual pod IP addresses and ports that the service is currently routing to. I told you I'm going to explain what is this routing table. Now it's time to explain you that. So for example, if you have a service with selector as F frontend and there are 3 frontend pods with IP addresses as this and this, all 3 pods are listening on container port 5000. The service endpoints would look like this: endpoint 1, endpoint 2, endpoint 3, and the port number 5000, 5000, 5000. Okay, and you do not manage endpoints manually. Kubernetes watches for change in pod status and automatically updates the endpoints list. When a pod becomes unhealthy, it removed from the endpoints list. When a new healthy pod comes up, it is added. Okay, I hope this is clear. So how do you get the endpoints? So we have Kubernetes commands for that: kubectl get endpoints and kubectl get endpoints frontend service, specific service. Okay, let's understand kube proxy. This is a one level deeper, I can say. And so kube proxy is a network agent that runs as a daemon on every single node in your cluster. It continuously watches the Kubernetes API server for changes. Specifically, it watches services endpoints being created or deleted. Okay. And when a new service is created, kubeproxy on every node sets up IP table rules for that service. These IP table rules intercept traffic destined for the service cluster IP and redirect it to one of the service endpoint. So it's like this: one IP table with bunch of IP addresses 1111111. Okay, just for example, I'm telling you. And the best part, we already have a load balancer. So the load balancing is random by default. This is the limitation of this IP table. It does not guarantee the request goes to the nearest pod or the least loaded pod. It randomly picks one of the available endpoints. Why this is happening? Because kubeproxy runs on every node and sets up same rules on every node. Any node in the cluster can accept traffic and route it to the correct pod even if that pod is on different node. So when a service is deleted, kubeproxy removes the corresponding IP table rules from the nodes. So if the kubeproxy is not clear to you, then you may not understand further concepts. So it's better I draw something and show you the kubeproxy again so that you can completely understand it. So let's open here. So this is our complete cluster with master node and 2 worker nodes. So currently what information we have is kubeproxy is a network agent, a long running process daemon that starts automatically on every single node in your cluster, in the master node and all the worker nodes. Okay, so as per that, we can have a kubeproxy here. So K denotes kubeproxy, K denotes kubeproxy, K denotes kubeproxy here. Now, what is the step number 2? The work of kubeproxy is to watch so all the kubeproxy instances opens a long live watch connection to API server. What we know, we have something called API server in the master node, API server. Okay, so it creates a long live watching connection between all the kube proxies and API server. It listens for any change to services and endpoints. So we have services here being deployed, S for services, and here services. Okay, so any change in the services, it keeps on watching. Whether you create any endpoint, whether you delete or do anything in the pod after connection to the service, it keeps on watching. Why they are watching? Because the moment something changes, all kube proxies are notified simultaneously. Now here's the step number 3. A user runs kube proxy, or a user runs kubectl apply minus -f service. Okay, dot YAML. When a user does this, the API server writes the new service to etcd. Okay, API server, we know etcd is a database, writes to etcd, which is a database, etcd, and also immediately informs the broadcast to kube proxy. Okay, on every node. So every node receives this signal, the real-time alert. The service gets a virtual IP. The service that we create right now receives a virtual IP, which is a ClusterIP. ClusterIP. Okay, for example, in our case, it is 10.96.0.1. So when it receives the virtual IP, what happens after that? Step number 4. So once they receive the virtual IP, kube proxy immediately programs something called IP table. Okay, IP table rules on its own node kernel. These rules says, let me just draw the IP table. So here we have IP table in the master node as the same IP address. Let me write that IP address. You can see in all 3 nodes, master, worker node 1, worker node 2, all 3 nodes, I have created one IP table and given them the IP address of the cluster IP. Okay, now this is maintained by the kube proxy. So let's just make a connection between them, slightly a better connection. Okay, slides, so they maintain this, and for example, suppose there are pods in this P. Okay, so these rules, what are these rules says in the IP table, that any packet, let me just write here, any packet going to cluster IP, intercept it. Okay, intercept it and rewrite the destination, rewrite the destination. So a packet going to a cluster IP, intercept it, rewrite the destination. This is what this IP table says. And this happens on all 3 nodes simultaneously, so the traffic can handle no matter which node it enters from. Now, how traffic actually intercepts? For example, there is a client pod trying to get some information or connect to the pod present here, this pod. Okay, so how it will happen? A client pod sends a request to cluster IP. It sends a request to cluster IP which does not have any existence physically. The moment that packet leaves the client, the IP table rules on that kernel intercepts it before it even hits the network and rewrite the destination to a real pod IP. Okay, so I know this is little bit clumsy, so let me just draw here so that you can actually understand. I hope with this you can able to understand much clear. So a client pod sends a request to cluster IP, which is your 10.96.0.1 port 80. Okay, that IP does not physically exist anywhere. The moment the packet leaves the client, the IP table rules on that node's kernel intercepts it. Okay, the rewrite happens, the destination to a pod IP is being added. This is called DNAT, Destination Network Address Translation. Okay, DNAT changes the destination IP to pod's IP and sends to the pod, which is pod A. So DNAT is very helpful here to change the or translate the IP. So this was the whole concept behind it. I hope this is clear to you. Let me open the notes again. So we have seen all this. I forgot to tell you there's an issue with this. So you might be thinking how it is deciding that the traffic should go to pod 1, not pod 2 or pod B. Okay, so this happens uh, because of static probability rules. So it randomly picks one for three pods. For example, there are three pods. Pod A gets 33% chance, pod B gets 33% chance, pod 3 gets 33% chance. This is a fundamental limitation here. IP tables is a firewall, not a load balancer. It has no awareness of pod loads, latency, proximity. For smarter balancing, we have other options. Okay, this is also important. When a service is deleted, kubeproxy removes the corresponding IP table rules from all the nodes. Now, traffic policy. Because the default random load balancing of IP tables is not always ideal, Kubernetes gives you control over routing behavior through traffic policies. Okay, now what are these traffic policies? They tells kubeproxy how to route traffic, and mainly there are two options, cluster and local. So the cluster option considers all ready endpoints across the entire cluster. Okay, so a request coming in on any node could be forwarded to a pod on any other node. This is the default behavior of cluster IP. Then comes the local. So kubeproxy only routes to endpoints on the same node. This is the key difference. Here it is written to any other node. Okay, why it is like this? Any other node. Okay, but in terms of local, it only sends to the active endpoints in the same node where the request arrived. This reduces cross node traffic and improves latency. But there is a disadvantage to this as well. So there is a trade-off. If there are no ready endpoints on the local node, the request is dropped, not forwarded elsewhere. Which means, for example, there are two pods, request comes in node 1 and there are no pods to be served, so requests get dropped. Okay, so you can configure both internal and external traffic policies independently in your service manifest. You can see in my previous videos I have told you, whenever somebody asks you in any interview to write any Kubernetes object, first write API version, kind, metadata. Okay, these three are, and spec. These four things are common. Inside metadata we will write name, front-end service. This is useful to get information easily because we are naming it. Then comes the selector. I told you we have selectors and we have labels in the pod. So app is front end, in labels the app also front end. Then comes the port TCP, protocol TCP, port 80, target port 5000. Then comes the internal traffic policy and external traffic policy. Currently we have chosen local as an option. Both internal traffic policy and external traffic policies are optional. You can set one without setting the other. Okay, or if you don't want local, you can write ClusterIP. Now we will discuss another very important concept, service discovery, how pods find the service. Previously what we have seen here is how the service finds the pod, okay, using label and selector. Then how these IP tables works. Then we have seen how this network actually translates using kubeproxy and IP table DNS with DNAT. Now it's time to see how pods finds service. Okay, Kubernetes supports two mechanisms for service discovery. One is environmental variables. So when a pod starts on a node, I hope you can imagine whenever I start speaking, I start reading my prepared notes, I want you to start imagining the concepts. So this is a node but nothing but a machine. Pod, nothing but a deployable unit, smallest deployable unit. Whenever a pod starts on a node, you applied kubectl -f pod.yaml. So whenever a pod starts on a node, the kubelet daemon on that node automatically injects environmental variables for every active service into the pod. Okay, the very important concept here. So for example, if a service called Redis master with cluster IP this on port number this, every newly created pod on that node will automatically get these environmental variables. So for example, there is a already running service called Redis master, and when a new pod is created on that node will automatically get these environmental variables. What are these environmental variables? Redis master service host, the same IP address of cluster IP, and port and TCP. Now there is an important limitation here. These environmental variables are only set at pod start time. If a service is created after pod already running, the running pod will not have environmental variables for that new service. So what does this mean? For example, there is this Qt node. There is already one pod running and there is no service. Now after the pod is being created, you create a service. This pod will not have the environmental variables for the new service which is being just now created. This ordering dependency makes environmental variables an unreliable approach for complex deployments. Then comes the recommended wait DNS. So Kubernetes runs an internal DNS add-on, typically core DNS, that automatically creates a DNS record for every service in the cluster. So what does that mean? Let's understand. So the full DNS format is service name.namespace.service.cluster.local. Pods in the same namespace as the service can reach it using just the short name. For example, http://frontend service. A pod in the default namespace can reach frontend service simply by calling this. Pods in a different namespace must include namespace in the name. Okay, so they have to mention the namespace production into the name. Okay, DNS is strongly recommended and most widely used approach to service discovery. It is simple, reliable, and has zero ordering dependency. Okay, let's understand the three major ports. We need to understand all these ports. What does that mean before we moving to cluster IP and other service types? So the first one is port. Okay, this is a port on the service itself. Okay, other pods like cluster sends traffic to this port. For example, if there is a port 80, then pod calling HTTP frontend service port 80 reaches to the service. Then comes the target port. This is a port on the container inside the pod. So we have this cluster, this node. Inside that we have a pod running. Then inside that we have the actual container which holds our application. So that is the target port. This is where the traffic ultimately arrives. Your application must be listening to this port. If the target port is 5000, your application code must bind the port 5000. If you do not specify the target port, it defaults to same value as the port. Okay, for example, if your application is listening at port 8080, you need to bind it to port 8080. Then comes the node port. This is applies on a node port and load balancer service types. Okay, if your service type is a node balancer, then this is applied. It is a port opened on every node in the cluster. Okay, and external users connect to node's IP and its port to reach the service. NodePort must be at a range of 30,000 to 32,767. Here's a quick example. So port, you define it as port 80. Service listens here inside the cluster. Then comes the target port you define here because your container listening here. Then comes the node port. You define a port range between 30,000 to 32,767. This is for the external users connection. Traffic path would be it hits your node port, then it hits your service port, port 80, then it forwards to your container port, port 50,000 for example. Then a very important concept we are going to understand is service types. There are different types of services. One is ClusterIP. So ClusterIP is the default service type where when you create a service without specifying a type, it gets ClusterIP service. A ClusterIP service is only accessible from inside the cluster. This is a very important point that I have written here. It gets a virtual IP address, ClusterIP. This is routable only within the cluster network. Nothing outside the cluster can reach this IP directly. So for example, you are defining a service and in that service you have mentioned the type is as ClusterIP. So it will give you virtual IP 19.0.9.1 that is only accessible inside your whole cluster network. You have worker node, you have master node and all these things. These cluster IP only accessible inside that workflow. So the use cases are when you want to use front-end pod communicating with backend pod, you can use the cluster IP. When backend application communicating with database, you can use cluster IP. Any internal microservice to microservice communication you can use cluster IP. Why? Because for example, there is two nodes N1 and N2 and your application is a banking service with multiple microservices. So you can have multiple pods running and one service running here and here. You can mention cluster IP as your cluster service type, and these pods can make easy communication using your cluster IP. So this is a possible use case. The cluster IP line is optional. It is default. If including it makes your intent explicit. For example, if you don't mention anything, it will by default take it as a cluster IP. This is the YAML of the service. We have API version, service kind as a service, metadata, front-end service, and spec, selector, app. I told you, again I'm reminding you, selector, and again in pod YAML file we have labels. Okay. And ports, we have protocol as TCP. Port, I told you we have ports just previously. Let me just go again and discuss here. We define port, we define target port, we define node port. Okay, so if we go back again, we define here port, target port, and type is cluster IP. Then what we have seen currently is the service types. Okay, so cluster IP we have seen. Another service type is node port. Now this is very important. NodePort builds on top of cluster IP. When you create a NodePort service, Kubernetes does two things. Okay, it creates a cluster IP as usual for internal access. It will work, but it opens a high port by default. The range is this, I told you, on every worker node in the cluster. So we have this where we have worker node 1, worker node 2. In the worker node, it opens a high port from range 30,000 to 32,767. A port is open, okay, in both the worker nodes. Now, external users can now reach the service by hitting any node's IP address on the node port. So, for example, this worker node IP address is 19.191.3.3. I'm just giving a random example for your understanding. It should be under this range, and people can reach HTTP, then node port, node IP, which is your 91.3.3, then colon any port number in between these two, in the range of these two. Then traffic hits the node. Kubeproxy intercept. We have just now learned about kubeproxy, how it intercepts. It using IP table rules, and it forwarded to the service cluster IP, which then routes it to pod. So I hope you understand the flow. So you hit this endpoint. Okay. After hitting this endpoint, you are actually hitting the IP of worker node. Okay. IP of worker node. IP of worker node. Then this worker node is transferring to kube proxy. Kube proxy, we have seen it intercepts and change the destination using the IP tables and forward this to cluster IP. Cluster IP. Okay. So what is this cluster IP? The whole machine. Okay. We have 93.3.3. Okay. It changes the destination port to cluster IP. Then it redirects to pod. This is how the flow works. The important point here is the node that receives the traffic does not have to be node running target pod. Kube proxy handles cross node routing. So we have seen that kube proxy sends the traffic. Okay, irrespective of checking whether the node having or pod having load or not. Using the IP table, it forwards. So the node we are hitting does not need that it is going to serve your request. Any other node can also serve. Let's go ahead and see the YAML definition for this. We have, again, I am reminding the reason I am again and again reading this YAML file, because once you keep on reading these YAMLs, it is going to be concrete in your head and you will never forget the slight changes between them. So we define API version, we define kind, we define metadata, name, spec, selector, app, frontend. Then protocol TCP, we open a port 80, we open a target port 5000. Again, I am asking you a question, why do we open a target port? I just now told you why do we open a target port. If you could answer, then you are listening. If you could not answer, please go back slightly. We open target port because this target port is actually the container port where the application is running. Then comes the node port. Node port, we define 3233. Okay, it's optional. Specify a port or let Kubernetes pick one. Type is node port. Okay, either we define or let Kubernetes picks. Okay, we define the type as node port. Previously, with the type as cluster IP, what did we do? Type is cluster IP. This is the only change we have done here, and extra changes we have mentioned the node port. When you use node port is usually for development, testing or on-premise clusters where you do not have a cloud load balancer. On Minikube as well, you can do Minikube service, front-end service. This commands open the service in your browser automatically, handles IP lookup for you. Again, I'm telling you in between the video, if you need one specific video on the practical hands-on, so I will be writing all these YAML files. I will be testing out all these commands. If you need that video, please comment. Okay, because that's going to take a lot of efforts. So I need your support in this so that I will do that. Then another type is load balancer. Till now what we have seen service types, one is cluster IP, one is node port, another one is load balancer. So load balancer builds on top of node port. So node port was built on top of cluster IP. Load balancer is built on top of node port. When you create a load balancer service, Kubernetes does three things. Okay, it creates a cluster IP internal access. Again, I told you this is by default. Then it opens a node port on every node. Again, we know this. It provisions an external cloud load balancer automatically. So this is something new to us, and this only works in cloud environment, for example AWS or GCP. In our here we call it as Elastic Kubernetes Engine, and here we called GKE, Google Kubernetes Engine. So the cloud load balancer, for example AWS application load balancer, and we have GCP external load balancer, gets a public IP address. Okay, distributes incoming traffic across the node port of all nodes. So for example, if I have these two nodes running in one cluster, okay, worker node 1 worker node 2, and they have 19.5.5, 18.5.5 to NodePort IP addresses. Again, externally in this whole cluster which they are part of, if we use load balancer as a service, we get another IP 22.2.2, for example. Okay, so this is given by cloud providers, and when somebody hits this, it redirects to one of the node IP, and that translates to a cluster IP and then hits your pod. So a very simple flow. Let me show you what are the exact changes. So we type as load balancer, we have target port and normal port. Protocol is TCP. So the major limitations is that the load balancer only works if your Kubernetes cluster is running on infrastructure that supports automatic load balancer provisioning. Okay. Typically a managed cloud provider, as I told you, AWS or GCP, if you apply this in a bare metal or local cluster with no cloud provider integration, the external IP field will stay in pending state indefinitely. Okay, the service will still work as a node port, but no external load balancer will be created. So this is the limitation. Let's understand external name. So external name is a special service type with completely different purpose. Instead of routing traffic to pod, it maps a Kubernetes service name to an external DNS name. So let's understand this, how it maps to an external DNS name. So when a pod inside the cluster calls the service name, Kubernetes DNS returns a CNAME recording pointing to the external host name. No proxying, no load balancing, just DNS redirection. Okay, so the use case is connecting to cluster applications to an external database like mydatabase.example.com, or connecting to a third-party SaaS API using stable internal name, or migrating external services into cluster over time. So we have a slight change here at this point. So we type is external name is mydatabase.example.com. Pod in the same namespace can now reach the external database simply by calling external database. Okay, and external service have no selector and no endpoints. This is crucial. You should remember, external name service do not have selector and no endpoints. There are no pods behind them. Let's understand external IP. It is not a service type like others. It is property you can add to any service. It maps a service to a specific IP address that routes to one or more of your nodes. So it's just an external IP mapping. External traffic arrives at that IP and port is forwarded to the service endpoint. So external IP addresses are not managed by Kubernetes. The cluster administrator is responsible for configuring the external routing so the traffic to that IP actually reaches the cluster node. So we can define spec, external IP and one IP address with a port. So we have seen all different types of service types. Okay, so let's move ahead a little bit and understand what is multi-port services. This is something that a lot of YouTubers, I have seen many videos, they don't cover in depth on services. And now you know it's era of AI, so people will ask you more in-depth questions on Kubernetes, because YAML files can be written through any AI tool. Okay, but the networking part is not written by any AI tool, because none of the company takes any responsibility if something goes wrong. So they prefer having an engineer who understand the YAML as well as understand what each line is going to do. So let's understand the multi-port services. A service can expose more than one port at a time. This is useful when your pod have containers listening on multiple port. So I told you that this is node pod, and your container. For example, a web server that serves HTTP on port 80 and HTTPS on port 443. So your container is serving to two different ports. So you can use multi-port services. This is the complete YAML of service. You have API version, kind, metadata, name as my service, spec, selectors, app, my app, type as NodePort, and you open the ports as name HTTP, protocol TCP, port 8080 for one, and container port 80. Okay, then the NodePort, again you define the same for another port. So what we are doing in a summary, if I have to tell you, that my service is exposing two ports within the cluster. Applications reach it on port 8080 and port 8443. Two ports, 1, 2. From outside the cluster, traffic arrives on NodePort with the port 31080 and 31443 and is forwarded to container port 80 and port 443. I hope this is clear. Let's look into port forwarding. Port forwarding is a lightweight way to access a service, pod, or deployment container from your local machine without needing a node port or a cloud load balancer. For testing purpose, you can use port forwarding. It is primarily used for local development testing debugging. You forward your local port on your workstation to a port inside the cluster. So this is your laptop. You forward your workstation to a cluster port. Then you open your browser on localhost that port as if application were running locally, and you can hit and test. So these are the commands: kubectl port forward service / frontend service port 8080 to port 80. Now you are forwarding the port 8080 to service port 80 and forward local port 8080 to a pod container port 5000 so that you can test your application. Then forwarding port 8080 to a deployment container port 5000 like this. All three commands make your application accessible in HTTP localhost port 8080. Port forwarding is an alternative to NodePort to quick testing. It does not require knowing the node's IP addresses and does not require a port to be permanently open on the node. It runs only while the kubectl port forward command is active in your terminal. Once you close the terminal, the connection ends. So it's time to wrap up all the theory part, and we will start learning some of the commands on services. So let's create a service YAML. So you can create a service YAML and you can run kubectl apply -f frontend service.yaml, or you can create a service like this. Creating with kubectl expose. The kubectl expose command creates a service from an existing deployment. Kubernetes automatically reads the deployment's label, selectors, and container port to populate service. So we are exposing the ClusterIP, kubectl expose deployment frontend, name frontend service port, target port, expose as NodePort. So you have to run kubectl expose deployment frontend, front name, type, port, target port. Then as a load balancer, create with kubectl create service command. So we are creating kubectl create service ClusterIP forward frontend. So we are creating a service type as ClusterIP frontend service with a port 80 5000, and then you are doing kubectl apply. This approach gives you more control, creates the service spec in memory, modifies it, and applies it all in one pipeline. For NodePort with specific port, you can mention NodePort. So let's see a complete deployment plus a service example. So we have a deployment here and we have a service here. So let's see how we are connecting it. So the deployment is for Nginx deployment. We have kind as deployment, metadata name as Nginx deployment, label app which is very important, is Nginx. Then we are creating 3 replicas, which means 3 pods are going to be created. And selector, we have match labels as app Nginx. Then template metadata labels app Nginx, spec container name is Nginx container, and we have a container port as 80. Then we create a service as kind service. We mention the metadata as Nginx service, which is the name of the service, and then in the selector we mention the app name as Nginx, which is routing to app name here. Then in the ports we open TCP port 80 because we are running in service port 80, and target port also 80 because container port is 80. Then we create a type as ClusterIP. So these are some of the important commands that you should be remembering. So I suggest not to try to remember. The moment you start practicing services and other important objects in Kubernetes, slowly you will be habitual to these commands. But for your reference, because I will be sharing you these notes, so for reference I have written couple of commands that will be helpful in debugging. Then comes the troubleshooting commands. So if a service exists and has the right type and port, you can do kubectl get service Nginx service, kubectl describe service Nginx service. Okay, if you want to check endpoint, then kubectl get endpoints Nginx service. If the endpoint list is empty, your service selector does not match any number, any running pods. This is the most common cause of service failure. Okay. Then kubectl get pods show labels. This command compares the labels shown on your pod against the selector in your service definition. They must match exactly. Check if pods are running. Kubectl get pods. Check container logs, kubectl logs, then pod name. Now comes the very important part of this tutorial, service versus ingress. So service handles network access to your pods. They operate at layer 4 TCP UDP, because in every service definition you can see we were mentioning port as protocol as TCP. Okay, so services works at layer 4 TCP UDP. A service gives your application a stable address, load balancing, and it is a fairly simple routing mechanism. That is all about the service. But then comes the ingress. Ingress is a separate Kubernetes object that operates at layer 7, which is your HTTP and HTTPS. It is a specifically designed manage external HTTP access to manage service cluster, usually a single point. Okay, so with ingress you can do things like route example.com/API to one service and example.com/web to another service. You can terminate TSL HTTPS at entry point and forward plain HTTP internally. Apply host-based routing, which is api.example.com to API service, app.example.com to front-end service. Ingress does not replace service, it works on top of them. And ingress routes external HTTP traffic to services. Those services then route traffic to the correct pods. So we have internet routing to making request to ingress controller, Nginx ingress, then it routes to service A, then pod, service B, then pod. We will see ingress because it's a completely separate topic. Just for your understanding, I have mentioned a slight introduction here. Let's go through the interview questions with answers. So what is the difference between port, target port and NodePort? I told you this is one of the favorite questions in Kubernetes. So the interviewer will definitely ask you to check your in-depth knowledge. So port is the port on the service itself. Okay, what clients inside the cluster connect to. Target port is the port of the container inside the pod where traffic ultimately lands. And the last, node port is the port opened on every worker node for external access where traffic flows. Okay, so traffic flow is like node port, then service port, then your container target port. Then the second question is, how does a service finds its pods? So a service uses labels and selectors. Each pod has labels. The service has selectors that specifies which labels a pod must have. The service routes traffic only to a pods with matching labels. This selection is dynamic. As pods come and go, the service automatically updates. Okay, then comes what happen if the service selector does not match any pod labels. I have already answered this question, so the service endpoint list will be empty and the service still exists, but there are no pods to route traffic to. Any traffic sent to the service will fail, reach no pod. Check, we can use kubectl get endpoint and service name to check the status. Then comes what is the difference between service and ingress. I told you a service operates at layer 4 TCP UDP and ingress works at layer 7 HTTP and HTTPS and provides path-based and host-based routing to multiple services plus TLS termination. Ingress works on top of service. It routes to services which then routes to pods. Use a service for internal and basic external access. Use a ingress when you need smart HTTP routing or want to expose multiple services through a single external IP. Then the last question, what is kubeproxy? What role does it play in services? So kubeproxy is a daemon that runs on every node. It watches the Kubernetes API server for service and endpoints changes and programs IP tables rules on each node to implement the service routing. Okay, so this is important. And when a traffic arrives at service ClusterIP or NodePort, IP table rules programmed by kubeproxy intercept and redirect the traffic to one of the service pod endpoints. So this is it for today. I hope the service concepts are actually very clear to you. Everything that we have seen are very crucial in terms of your interview and in terms of the understanding of service, because a lot of things depends on this. So I hope you understand. If not, go ahead and watch it again. No worries, until and unless you learn it thoroughly, keep watching it.